Hello, everyone. Welcome to the final and afternoon sessions of today. So let me first introduce our first speaker for the session, Federica, on quantum simulation of string breaking dynamics. Take it away.
Right. Thank you. Thank you for being here for the Friday afternoon session. I really appreciate. I'm really excited to present this work. That is the result of a collaboration with the experimental group at Duke and our theory collaborators in the University of Maryland and Oxford. I want to start by explaining, of course, what string breaking is. I know that probably not many people are familiar with this idea, so let me try and give you a little bit of context. So string breaking is an important phenomenon in quantum chromodynamics. Quantum chromodynamics describes the physics of quarks and gluons. So as you probably know, you don't usually find quarks and gluons in nature because matter, as we know it, is rather made of protons and neutrons. So how do quarks and gluon come together? How do their interaction result in the formation of these composite particles? So this is, in general, a difficult question. And in the last 50, now a bit more than 50 years, people address these questions using Monte Carlo simulation on the lattice. And this is a very powerful tool. It allowed for the calculation of masses of protons and neutrons. It allowed for the calculation of many properties of quantum chromodynamics. And more recently, there has been a lot of interest in trying to understand if this classical Monte Carlo simulation can be complemented by quantum simulation. Because there are some regimes where classical Monte Carlo simulations encounter the same problem. And so, for example, it's hard to simulate real-time dynamics. It's hard to simulate regimes in extreme conditions that are important for cosmology or in astrophysics, for example. So these are, for example, some reviews that try and address this question, like, can quantum simulation be useful in this context? Now, as I said, string breaking is what I'm going to talk about. And so to understand what it is, let me first explain what is confinement. So as I said earlier, we don't find quarks, isolated quarks in nature. We find them confined in composite particles. And so this is an illustration of one of these composite particles. So these red and blue balls that you see here. Okay, yeah. These ones represent a quark and an antiquark, while this blob here is essentially a gauge of a flux tube. It's what I will later refer to as a string. So this gauge flux tube, this string, has an energy that's proportional to its length. Okay, so it's proportional to R, which means that quark and an antiquark experience a potential, like they have an energy that grows linearly with their distance. So, and this proportionality constant is what we call a string tension. Now, this picture holds for a good range of the distance R. So you see here in this plot this linear dependence of the energy on the distance. But as you go to longer distances, this linear dependence breaks down and there is a saturation. And the way to understand this is essentially the following. So what happens if you reach a certain threshold in the energy is that you can produce 2 additional particles out of the vacuum. This is energetically favorable, and you break the string into smaller strings, basically. And now you can keep pulling these charges apart, and energy will not increase. Okay, so this phenomenon, the fact that this string breaks when you produce 2 more particles out of the vacuum, is known as string breaking. Now, we would like, of course, to have a quantum simulator for this. We don't have a quantum simulator for quantum chromodynamics. That's too difficult. But, well, the good news is that confinement and string breaking occur also in much simpler models, like one-dimensional models. And this is what I'm showing here are a few examples of work that studied string breaking in one-dimensional systems. Like these are numerical simulations. So these, I don't want to go into the details of these models, but the essence is that these are all simple models that are much more treatable. And in fact, what I will talk about today is precisely one of these models. I will talk about the Ising spin chain in one dimension. Okay, so this is the model of interest. We have Ising ZZ interactions. There is a transverse field G, and there is a longitudinal field H. Now, what does it have to do with quarks and strings? Well, the idea is that domain walls here are the excitation. We're in the ferromagnetic phase, and excitations are these domain walls, and the spins, this region of down spins in between those 2 domain walls is basically a string. So these spins are pointing in the wrong direction, so there is an energy cost associated with them, and this energy cost it's proportional to this length. Okay, so in this case, it's a very simple calculation. If G is 0, then the energy cost of having 2 domain walls at a distance L is 4J, that's the energy of 2J is the energy of each domain wall, plus 2H times L times the distance. Okay, so we have now this linear potential, and this 2H plays the role of the string tension. And now, this linear confining potential has actually been studied already in a quantum simulator. Guido talked about this morning, like he briefly mentioned this work. That this was a quantum simulation with trapped ions. In that case, this Jij is long range, but for what I will discuss next, this is not very important. And in this quantum simulator, they were able to show the effect of confinement in the dynamics, for example. Okay, so confinement was demonstrated in trapped ions. Now, can we observe string breaking? So this is what we wanted to do. And how do you do this? Well, first of all, how does the string break? So the idea is that you start from this string configuration, and you want to achieve this configuration where you have 2 additional domain walls that essentially screen the string, and now the energy is simply the one given by these 4 domain walls. So in this case, you go from a region of down spins to a region of up spin, and the energy, if you look at the energy as a function of L, this is very similar to what I showed earlier, linear growth, and then there is this saturation, this crossover. Now, and this crossing point is precisely when the energy of the string compensates the energy of 2 domain walls. Now, so this is the same plot, the same idea. There is a length at which you observe string breaking, but because we cannot really tune the distance of the string continuously in this experimental setup, we're on a lattice, so it's actually more convenient, rather than changing the distance, it's more convenient to change the string tension. And if you think about it, the energy is proportional both to the distance and to the string tension. So also, if you increase the string tension, you will see that at some value, like what we call this HC, then there is this same kind of physics, this crossover, and then you will observe a string breaking at these values, at this specific value of the longitudinal field. Okay. So how do we do this in practice? Well, the idea is that, okay, we're not changing the length of the string. We keep essentially these external domain walls fixed. Okay, we only allow for the internal spins to flip. So this is basically the reason why here in this Hamiltonian, I only have a transverse field on these L sides, J from 1 to L, while all the external spins are essentially frozen in their configuration. Okay, so in this sense, these two domain walls are two static charges, and so it means that now we don't need to simulate the entire system. It's enough to simulate just the internal spins. And the effect of the external spins is essentially gives rise to a longitudinal, side-dependent longitudinal field, this Hj effective. Okay, so now we need to simulate this spin chain, this Hamiltonian of L spins with some inhomogeneous longitudinal field. And, well, the good news is that our experimental collaborators are actually able to engineer a tunable longitudinal field of this form. Okay, so what do we expect to observe? Let's start, first of all, from the spectrum. So, as I said, this is the Hamiltonian. This is the low energy spectrum of this Hamiltonian as a function of the longitudinal field H. And the color represents the demagnetization. So you see very clearly here that there is for H, in the absence of the longitudinal field, the ground state is the string configuration. And the broken string is the first excited state. As you increase the longitudinal field, there is this avoided level crossing here, and this is basically the string breaking point. Okay, and there is a small gap here, this delta C. Now, it's quite easy to convince oneself that this HC goes as 1 over L. This is basically from what I showed earlier, this calculation of the energy of the string. And this gap is exponentially small in L. So the idea is that essentially these two levels differ by L spin flips. So the matrix element between these two will be exponentially small in L. Very good. So, okay, so we want to observe this in the experiment. And the idea, what we do is the following. So it is to start from this string or the broken string configuration. So this classical configuration, and then slowly turn on the transverse field. Okay, so not the longitudinal field, so we're not going across this avoided level crossing, we're turning on the transverse field, and so then we measure the energy. The idea is that we do this adiabatically. And then, okay, so if you measure the energy, what should be now this string or this broken string state, you actually see that as a function of the longitudinal field, there is indeed this level crossing. And now, okay, the theory is this one, but if we include the spin flip error in our theoretical simulation, you see there is a good agreement with the experimental points. Now, as you can see, this works. This gives the correct crossing point, but it's actually not very easy. It's not really easy to compute this crossing point in a very accurate way. So we then considered a more accurate method for this. So, and the way to do this is through a quantum quench. So what we did basically was to prepare this string state and then evolve with some Hamiltonian that at some fixed value of the longitudinal field. We don't change this in time. And then we measure some observable that I will describe in a moment. And we will see that this observable as a function of this longitudinal field has a peak precisely at the string breaking point. And later I will show how we observe slow thermalization. And the second part of the talk, instead, I will talk about a ramp where we ramp H across the string breaking point. Okay, so let me first explain this quench and how we measure the string breaking point. So this is the spectrum that I showed earlier. And the idea is that at the crossing, the eigenstates are these superpositions of all up, all down states. Basically, morally speaking, G is G state kind of state. So if we quench precisely at that value of the longitudinal field, we expect to see oscillations between the all up and all down state. And what this means is that if you look at the evolution of the magnetization in time, okay, if you quench exactly at this value, you will see large oscillation of magnetization going from negative to positive, while if you're away from that point, the magnetization will essentially not change. So we plot the maximum of the magnetization after a certain time after the quench, and we observe that indeed there is a peak precisely in the region near to the string breaking point. So this is a more accurate measurement of the value of HC. Now, we do this for a string of 5 spins. Now, this is hard to do for longer strings, and the reason is twofold. First of all, the peak gets narrower and narrower with L. And the second reason is that you need a very long time, basically because the oscillation, the period of the oscillation is given by the gap, and the gap is closing exponentially with L. Okay, but for 5 ions, we can actually show this, and we can observe these collective oscillations. Now, I will not go in the details, but I just want to mention that for longer chains, we study similar quench away from resonances, and we study also how the string breaks in this case, and we observe that there is a very slow relaxation to thermal equilibrium. So yeah, if you're interested, we can ask me later, we can discuss this. But I actually want to go to the next point. Okay, so as I mentioned, we use the quench to find the string breaking point by observing essentially this resonance in the maximum value of the magnetization, and we observe slow thermalization. Now, the next thing we wanted to understand what happens if you actually start from zero longitudinal field, so without any string tension, and then you increase the string tension linearly in time, and you go across the string breaking point. What will you observe? So this is what I'm going to discuss next. So, okay, so the protocol is the following. We first turn on the transverse field. The idea is that we can do this adiabatically. There's a gap. It's quite safe. We don't need to go too slow. And then we turn on the longitudinal field. And in turning on the longitudinal field, we cross this string breaking point with the level crossing. And what you expect to see is that as you cross this point, depending on the speed of this ramp, you will see a different behavior. In this case, for example, of the demagnetization, you see that if the time is long, so if you're very slow, you're close to the adiabatic limit, you will see that magnetization changes sign from negative to positive, right? You follow the ground state, but if you're too fast, then you essentially, magnetization doesn't have time to change. So essentially what you observe after this ramp is basically described by Landau-Ziner type of physics. Okay, so let's look at the experimental data. So this was the spectrum I showed earlier. So to make it easier for us to observe this kind of physics, we chose a slightly different profile of the ramp. So rather than using a linear ramp, we use one that slows down as we go through the string breaking point. So now the energy profile in time looks like this. And so here in this plot, you see basically the distribution of the number of bit flips. So 5 means all spins up, 0 means all spins down. And the colors represent the different speeds of the ramp. Okay, so here you see that if you stop essentially here, so before the string breaking point, there is no dependence on the speed. This is quite expected. You're basically adiabatic. Now, if you stop instead here, so basically at the string breaking point, you start to see some dependence on the speed. And as you go past the string breaking point, you see more and more this dependence. So for example, here at 0.5, you see that, so for this value of the speed, so it means if you go very slow, most of the spins will be pointing up, so the string is broken, while if you're very fast, like this yellow line, most of the spins are pointing down, so the string doesn't break. Okay, so to give a bit of a more quantitative estimate of this, we tried the following protocol. So we did the same as before, but now we turn off the transverse field. So, and in this way, we can essentially map back the string and then broken string state to the all up and all down state. And so here I'm plotting the probability of finding the all down, so the string state, or the all up, the broken string state, at the end of this double ramp. And this is the probability of the other states. And this is as a function of the time of this ramp. And so you see again that the probability of string breaking grows with the time of this ramp. If you try and do the same thing, so this was for 5 spins. If you try and do the same thing for 13 spins, you don't see anything. And once again, the reason is the same as before, because if you have a longer string, then this avoided crossing, like the gap there is very, very small, so you're basically always completely diabatic. And so as you see here, you'll always stay essentially in the string state. You'll never end up in the broken string state. So, okay, for longer strings, the gap is too small. The evolution is diabatic. So can the string break in this case? Well, the answer is yes, but you will need to go to a larger value of the string tension. So here I'm plotting again the spectrum. This is this first avoided level crossing, but I'm also plotting the spectrum for larger values of the longitudinal field. So now this is the broken string state, this is the string state, but there are also many other states, and these are what we call the bubbles, meaning that those are states that are only, where the string is only partially broken. Okay, so, and the idea is that if you then take a ramp that goes across, for example, this range of h, you will observe breaking because of this bubble. So the string will break in smaller pieces. So this is what we do. We do, again, the same kind of ramp. And now we look at what happens. Like, this is the magnetization. Like, this is the position, this is time, and this is for different values of the total evolution. And as you see, you tend to observe string breaking at some value of h that is smaller and smaller as you go slow. Okay, so the slower you go, the smaller the value of h where you observe string breaking. So you go from negative to positive magnetization. And the other thing we observed was that you can also try and understand the properties of these bubbles by looking at the size of the largest domain of upspins. So what I'm plotting here is the distribution of the size of largest domain. So this is the probability, essentially, of having a largest domain of size 0, 1, 2, 3 as a function of time. And again, so here you see that this is for longer and longer times. So at long times, this distribution, like after the string breaks, the distribution is peaked at some large value of this size. So it means that the string breaks by forming large domains of upspins. While if you go very fast across this string breaking point, you will see that the distribution, so these bubbles tend to be very, very large, very, very small, sorry. Okay, so this is how we characterize string breaking in this case. Actually, I'm with time. Maybe I will skip this. Okay, maybe I will quickly flash this. I think I have time. Okay, so the other thing we did was to try and observe the saturation in the potential as a function of time. So we measured the energy essentially across the same ramp. And this is the energy in the presence of the static charges. Well, this is the energy without the static charges. So the way to compute the potential is you take the difference. And as you see here, so this is what is plotted here is the difference between the two. And so this is for two different values of the evolution time. And so in both cases, you see that there is some kind of saturation. So it first grows linearly, then it tends to saturate, and the slower you go, so the largest this t, the sooner you start to observe this saturation. So once again, slower means you break at a smaller value of the longitudinal field. Finally, let me mention that this phenomenology of string breaking is very closely related to another phenomenon that's called the false vacuum decay. So the idea is that if you look at the phase diagram, so this is the magnetization of the ground state as a function of a transverse and longitudinal field. So the avoided level crossing that I showed were essentially in this direction as we change h. So you see that basically you can think of this as a first order phase transition. Only, okay, this value of h is going to 0 as 1 over L. But the physics is essentially the one of a first order phase transition. And so this means that as you go across this first order phase transition, you end up, so if you started from the ground state, you end up in a metastable state. And it is known that the physics of this metastable state, you expect essentially a decay. This is the false vacuum decay. We studied this in this paper some time ago, and also there's been a lot of recent progress in the field. I guess you will hear about some of this later this afternoon. So to summarize, I first show you how we can use a quench to find the string breaking point, and how the quench dynamics also shows this slow thermalization that you also observe in generally confined systems. And also, well, that this method works well for small strings, I forgot to say. And then I showed you how we studied the dynamics if we ramp up the longitudinal field across the string breaking point. And this is described essentially by Landau-Zinner dynamics for small strings. So we observe complete string breaking, all spins going from down to up. And for longer strings, this string breaks by forming bubbles. And finally, like, slower evolution leads to a smaller value of h where we observe string breaking and larger bubbles. So with that, I want to thank my collaborators, both on the theory side and experimental side. And I want to also advertise another work we did with the same team that is essentially a proposal for a quantum simulation of meson scattering. So mesons are precisely these composite particles that I showed at the beginning. So yeah, if you're interested in this work, you can find it in arXiv. The string breaking papers are not yet on arXiv, but they should be out soon. And we also studied something similar in a previous paper with Alessio Rhode. And with that, I thank you for your attention.
Questions from the audience?
Thanks for the nice talk. So I was wondering, is it possible to see this in the light cone structure of the correlation spreading, the string breaking, or do you really need all of these local fields and so on?
Yeah. So it is possible to see it also in the correlations. Well, for example, for small strings, you can the fact that you go from all down to all up, and you essentially have a superposition of these two states. You will see in the fact that you have that you essentially have this kind of long-range correlations developing across your system, and I guess similarly also in for longer strings, we didn't study this in detail, but also you will see. So for example, we were expecting to see this kind of peaks in correlations corresponding, for example, to the resonances, and this we could observe. Yeah.
Right. Still have time. Any more questions?
Thanks for the nice talk. I guess I have maybe a naive confusion. At the beginning of the talk, you talk about there are super complicated models, and there's a string breaking phenomena, and they also arise in simpler models. So the question is the idea eventually will kind of extend this to the models that will be far beyond classical simulation, or
Yeah, that's a great question. Yeah, indeed. The fact that you have confinement and string breaking in this model, like in the Ising chain or in other one-dimensional system, is not really surprising. You can understand it classically. I showed you, in the classical model, you also have the same thing. So what we wanted to understand was if the fact that you have these quantum effects, like this kind of Landau-Zinner dynamics and so on, could be used. First of all, it had an effect on the dynamics, and I think, yeah, the idea for the future would be that, okay, in other systems that are way more complicated, where it's actually hard to understand, like, how does a linear potential arise? Should you expect to observe string breaking? Then you can use similar tools to try and characterize it through a quantum simulator, at least.
I think we have time for one more question, if there's any.
Great talk. Are there prospects for quantum simulation of string breaking beyond Ising?
Yeah, so I think like one of the talks that was in this was scheduled for today was actually about string breaking in a two-dimensional system. So yeah, in this case, well, we focus on this case because the experiment was already there and the confinement was already demonstrated there. But yeah, I think that's actually the most interesting prospect would be to go to other models where the mechanism is not simply understood from classical intuition.
All right. Okay, let's thank Federica again and welcome the next speaker.